Now let's compare them. First, let's compare their space consumption. There are two cases. When the graph is sparse, it means there are only a few edges. So we know that adjacency list is theta of V plus E, and matrix is theta of V squared. Then if the number of edges is quite small, that is, E is smaller than, maybe very smaller, much smaller than V squared, then this list requires less space than the matrix. But if the graph is dense, that means E is V squared. Then their space complexities are the same. This is theta of V squared, and this is also theta of V squared. But there is a big constant inside this theta notation. Why? Let's compare these two representations. What is the constant hidden here? Look at this. Look at these values. There are only zeros and ones in this matrix. So it's a bit matrix. So we need only V squared bits. But how about this? Each entry stores an integer. It means at least this is a 32-bit word. So additionally, we store pointers. So to store an edge, we need at least 64 bits. So they are different. And look at this. Edge present test. Edge present test is a query asking if an edge exists or not. Then adjacency matrix takes theta of one time, but the adjacency list requires big O of V time. Why? Okay, in this case, we can access the entry ij in constant time. If one is stored, then there is an edge. Otherwise, there isn't an edge. So it takes constant time. But how about this adjacency list? We should go, let's say it's 4, 1. Then we have to check out this adjacency list of 4. Then we have to scan this list to check if one is stored or not. So one is not stored, but we have to scan all the whole list. So in the worst case, the list can be as long as big O of v, theta of V. So its running time is big O of V. And another question or query is like this: listing or visiting all edges. Okay. Who? Kim Jong-bin. Okay, can you explain this? So we have to visit or list all edges in the graph. If we use an adjacency matrix, it takes this time. Or if we use, yeah, what is it?
매트릭스는 연결된 거 다 확인하려면 리스트하면 5개 리스트는 그러니까 결국 각각의 노드들을 다 한 번씩 훑어봐야 되니까 노드의 개수가 V 플러스 2개니까.
Okay, the main difference is adjacency list stores only existing edges. Okay, so in this time complexity, we can list or visit all edges. But in the case of adjacency matrix, there is no way to extract existing edges. We have to check every bit in the matrix. So it takes theta of v squared time. Okay, then let me explain some extensions of the representations. This is a weighted graph. In this graph, every edge has its weight. The weight of this edge is 2, and the weight of this edge is 4. And this is the adjacency list of this weighted graph. And this adjacency list is different from its original form. What's the difference? 신경식. What's the difference between this and the previous one? 어미송. Yes. A new field is added in each node. Look at this field. So this node stores this edge from A to B. And then there is a new field to store the weight of this edge. So by extending a node with a new field to store the weight, we can simply extend this adjacency list. And this is the extension of adjacency matrix. Weight is stored instead of 1. So another question. So if we use a weighted graph, does this work? Yes, not bits, maybe 32 bits, because each entry should store an integer, so at least 32 bits, or 64, or if the values are small, then you can use 1 byte or 2 bytes. It depends. And then transpose of a matrix. Okay, read this page and try to understand the definition of transpose. Swap rows and columns. More exactly, Tij and Aij and Aji are swapped. If the graph is undirected, the adjacency matrix, the transpose of an adjacency matrix is the same as the original adjacency matrix. Why? Because it was symmetric along the main diagonal. Okay, then what if the graph is directed? What is the result of the transpose of its adjacency matrix? 김현준. So we have a directed graph, and we have an adjacency matrix of the graph. And then we take the transpose of the matrix. So which graph does this graph represent? Yes, the edge directions are reversed. Okay? Understand? So if these two things are swapped, if this is 1, in the transpose matrix, this is 1. So edge directions are transposed. Some self-study questions. Okay, now I'll explain breadth first search and depth first search. Let's start with a simple example. A tree. This is a tree. We are going to search this tree from this vertex. And first, let's search using the BFS. What is the order of visit if we use the breadth first search? 문경식. 박용호. 이동우. The order of visits if we use the BFS. Yes, then. Yes, 1, 2, 3, 4, 5, 6, 7. So this is the BFS order. BFS is the level order. First, we start from here, it's 1, and then the nearest vertices from the source are visited. So these two vertices are away from this vertex by one edge. So they are visited, 1, 2, 3. And then these vertices are visited. Okay? You may visit in this way, 1, 3, 2, 7, 6, 5, 4. That's fine. Or 1, 2, 3, 7, 6, 4, 5. So in the same level, their permutation is fine. That's BFS. And then DFS. 이정우. DFS. 이종하. Okay. Enumerate the order of vertices. 1, 2, 4, backtrack, 5, backtrack, and 3, 6, backtrack, and 7. Yes, DFS is, you can go as long as there is an edge unvisited. Otherwise, you backtrack. That's DFS. Okay, so I'll explain BFS in a graph. First, I'll define distance of vertices. In this case, distance between vertices. The distance from a vertex U to another vertex V is the number of edges in the shortest path from U to V. So look at this example. The distance from S to V is 2 because this is the only path, so it is the shortest path, and there are only 2 edges in the path, so it's 2. So I'll explain the BFS. We are given a graph and a source vertex S. It explores the edges to find every reachable vertices. It discovers vertices in the increasing order of distance from the source. It first discovers all vertices at distance 1, then distance 2, and distance 3, and so on. In this example, we start the BFS from S. What are the vertices with distance 1? 정명수. So distance 1 vertices, what are they? RW, yes. First we visit R and W. Distance 2 vertices. V, T, X, yes. Then we visit V, T, X. And look at the color. So first, unvisited vertices are white. And then newly visited vertices are gray. And vertices whose adjacent vertices are already visited, they are black. And then finally, U and Y are vertices at distance 3. And during the breadth first search, it also computes the distance of vertices from the source. So we calculated the distances of each vertex, and we store it in this field, U.D. So D means the distance from the source. So each vertex has this field, and it has another field, the predecessor of vertices in this graph. Look at this. Breadth first search is used to find the shortest path from the source. Okay, then this is the shortest path distance. And we have to know the distance, we have to construct the shortest path from the source. In this case, what is the shortest path from S to T? 한상현, what's it?
From S to W and from W to
S, W, T, right? 강인구, what is the short path from S to U? They are the distances. You have to name the vertices. 박성현. SWTU. Huh? SWXU. That's fine, but in this breadth first search, we used these edges. So these edges are colored in this case. Then what is the shortest path from S to Y? 윤호상. SWXY. Okay. So if we enumerate shortest paths in this way, then we need theta of V squared space. Because each shortest path can contain V vertices. So there are V shortest paths, so the space consumption is theta V squared. That's too much. Instead, we store only the predecessor. Then we can construct the shortest path in the the construction time is proportional to the shortest path length. Look at this. So we know that the predecessor of T is W. So T, W. Then let's start from U. U, T is stored. So we know that the predecessor of U is T. And then check this. The predecessor of T is W. And in W, S is stored. It's the predecessor of W. So then we can construct the shortest path. If we store the predecessor of each vertex, the space requirement is reduced to theta of V. Right? Yes. So we denote the predecessor by U dot pi. And this graph is called the predecessor graph. So we use only these edges. And this is a tree. So it is called the breadth first tree. So now I will explain the BFS in detail using an example. This is the pseudocode for BFS. It looks quite complicated, but in 20 minutes, you will find out this is very simple. It's a magic. Let me explain. Okay, we will run the BFS on this graph. Initially, all vertices are white, except the source. And white vertices are undiscovered. So their distance is infinity. And the source vertex is discovered and its distance is 0. And the first thing to do is put the source vertex in the queue. This is a queue whose name is Q. Okay, then we do this repeatedly. And each loop is like this. We extract a vertex from the Q, in this case only S, because only S is stored, we extract X from this Q, S, and then visit the adjacency list of S. And then, while scanning this list, we visit unvisited vertices. In this case, R and W are unvisited, so we mark them as visited, and their distances are 1, because the distance of S is 0. And then they became gray, and finally they are in-queued. They are stored in the queue. Okay, white vertices are undiscovered vertices, and gray vertices are newly discovered vertices in the queue. And black vertices are finished vertices out of the queue. And now we do the same thing repeatedly until the queue is empty. So what is the next step? The next step is this. We extract R from the queue and then scan this adjacency list of R. Then there are S and V. First, we check S first. And it is already visited. So we don't do anything. We do nothing. And then the next vertex is V. It is unvisited. So we visit V and store V in the queue. So R is removed from the queue and V is added in the queue. And then remember that the predecessor of V is R and the predecessor of R is S. Don't remember this. Sorry, don't forget this. Sorry. But you didn't notice it until I speak it again. Okay, then what is the next step? S is already visited and T and X aren't visited. So we don't do anything on S, but what do we do on T and X? Okay, so first visit them and in-queue them. So visit them and T and X are in-queued. Okay, T, extract T from the DQT and U is visited. And then X is visited. Among these 4 vertices, only Y isn't visited. So we visit only Y. And then U and Y, nothing, nothing, done. Okay, now you can understand this pseudocode in 1 or 2 minutes, I'm sure. predecessor is undefined, yes. So the first 4 lines are the initialization step for all vertices except the source. They are white and their distances are not defined and their predecessors aren't defined. Okay. Hong Dong-gyun, what's the next 3 steps from 5 to 7?
시작 소스를 방문했다고 표시.
Yes, the source vertex is visited and then it's that
디스턴스 영어로 하고
as distance is 0 and
이전
no predecessor because it is the start vertex, source vertex. And then 2 more things, 2 more lines.
그 소스를 큐에다가 처음 넣어줍니다.
Yes, initialize the queue and put the source vertex in the queue. So after this line 9, this is the state of the BFS. All vertices are white except the source, and the source is gray with distance 0. And from here, we do this loop repeatedly until the queue is empty. Yes, we visit every vertex in the adjacency list of the vertex which is extracted from the queue. And then if it is visited, we skip it. But if it isn't visited, we make it gray and set the distance and set the predecessor. And what is the last step?
그다음에 맨 마지막 플래그요.
This in queue.
그 방문 해야 될 거를 이제 큐에 가져가지고
Yes, we put the newly visited vertex in the queue. And after this loop, okay, after this for loop, we do this. What is it?
방문이 다 끝났으니까 그냥
Yes, we change the color of U black. It means it is out of the queue. I don't think this is difficult if you try some examples. And let's analyze the running time. The initialization takes theta of v time, and the while loop takes big O of v plus e time. Yes, so consider a undirected graph. Then we have to visit this direction and this direction. So there are 2 directions, so that's why and most twice. So the total running time is big O of v plus e. And my last question, why we have to add and most? Based on your explanations, they should be once and twice. In this case, it means 0 or 1 or 0. Yes, why? Yes, if a graph is disconnected, there are some vertices not reachable from the source. So we don't visit those vertices. So those vertices are not examined. And edges between those vertices are not explored. So they are at most ones, so that's why it's big O, not theta. And it's possible, and it is possible to select an unvisited vertex and start the BFS again. And we do the DFS. But when we use the BFS, the purpose is to find the shortest path distance of vertices from the source. So it is meaningless to check the vertices not reachable from the source. Okay, then I will explain the first part of the DFS. The color conventions of DFS is the same. Every vertex is initially white, which are not discovered. And the vertex is grayed when it is discovered. And the vertex is blackened when it is finished. That is, when its adjacency list has been examined completely. So this color convention is the same as in BFS. And there is something more. There are timestamps. Every vertex has two timestamps. Its discovery time and its finishing time. Discovery time is the time when the vertex is grayed, when it is visited. And the finishing time is the time when it is blackened. Okay, and let me show you an example. When we run DFS, we randomly select the start vertex. And start vertex is meaningless. It's just a vertex starting DFS because we don't compute the distance. A start vertex is just a vertex to start the DFS. In this case, vertex U is the start vertex. And it is grayed at time 1. So this is the discovery time and this is the finishing time. And then in DFS, we first check the outgoing edges of U and we follow any one of them. So we may follow this edge or follow this edge. In the example's choice is follow the edge from U to V. So V is visited at time 2. And then this is different from BFS. We search, we find an outgoing edge of V instead of U. And then it has only one outgoing edge. We follow this edge and then Y is discovered at time 3. First, we check if there is another outgoing edge. But in this case, it was the only outgoing edge of X. So it doesn't have any more outgoing edges. So in this case, we backtrack. So backtrack. Before we backtrack, we make the timestamp of X. Its finishing time becomes 5. 1, 2, 3, 4, 5. Actually, this is a counter, not an exact time. And then we backtrack. So visited and it has no other unvisited vertices, we backtrack again. And its finishing time becomes 6. And becomes 7, its finishing time is 7 and backtrack. And then what do we do on U? 관다음. Now we are here. And we are here from V. And what do we do from here? But yes, first we follow this edge, and x is visited already. So it's time to finish view, and its finishing time is 8. So this is the first loop of DFS. But DFS doesn't stop now. It does until all vertices are visited, even though they are separated. Then 2 vertices are unvisited, but we select one of them arbitrarily, and then start DFS again. And this example choice is W. And then its discovery time is 9. First, we follow this edge, and then Y was already visited, so backtrack. And then we follow this edge, Z is unvisited, so we visit Z at time, what? 10. Yes, 10. And we check this edge, useless, finishing at 11, and backtrack, and finish at 12. So all vertices are visited and finished. And these are timestamps. And look at these edges. The shaded edges are edges used to find vertices. And the dashed edges are useless edges. So in the breadth first search, we said these are 3 edges and others are non-3 edges. It is true. These are 3 edges, and these and dashed edges are non-3 edges. But there is a difference. The predecessor subgraph is not a tree. It's a forest. Why? 김현준. Why? Yes, because the graph was disconnected. We cannot create one tree. They can be separated. That's why it is a forest. Okay, up to now, you understand the basics of the DFS. I think you already studied DFS in data structure course, but I don't think you learned the timestamp of the DFS, and this timestamp is very important. If we use the timestamp, we can do a lot of things with the DFS. Let me explain the use of timestamp on Friday. Okay, any questions? Okay, this is a DFS on a directed graph. So in an undirected graph, we should visit both directions. So that's the only difference. Okay, see you on Friday.